this chapter. Okay. I think it would be better if we discuss the test one. All right. Let's discuss the test one first, and then like move on with test one, and then we go on with the sequential circuit. Okay, let's move on with the combinational part. Right. So, the first part of these questions, the first part of test one, question one, I think personally, I think it's not really hard because the Q format, two of them are positive numbers, and when you do the Q format, when you adding the fraction number, the fraction number is not that big. It's just 1/4, 1/8. All right, so let's go on the first one. Okay. The first one is you are given minus in decimal. So you want to find this number in sign magnitude, one's complement and two's complement. Right? To find minus 45 in the sign magnitude. So for sign magnitude, we just have to copy the bits of 45 as the normal binary, and then the MSB will become 1. So 45 in binary is 32. Plus 8 plus 4 plus 1. Okay. This from left, it's 0, 1, 1, 0, 0. Then the MSB must be 1. So that is how we write the sign magnitude. And then for one's complement is the normal binary. You flip it once, right? So the MSB is 1. The MSB is 1. Okay. This is for sign magnitude, this 7-bit left is equal to the normal binary. So we just take this number and flip it once. 1, 1, 0, 1, 0, 0, 1, 0. And then for the ones complement, you add 1 to it. So it's 1, 1, 0, 1, 0, 1, 1. Right? Okay. So that's how the question when we are given a decimal number. Second question is you're given a sign magnitude number and you want to find the decimal, one's complement, and two's complement. So now let's first find the decimal number. So this 7 go to the normal binary, and this is the sign bit, so it's negative. Okay, this number is negative. So the normal binary says it is 64 plus 8 plus 2 plus 1. Okay, this is 4 plus 8 plus 2 minus sign bit is 1 here, right? One's complement 1 is negative, the sign bit is 1, and then this part is flipped once. So 0, 1, 0, 1, 0, 0. Okay. And then the ones come. So 1, 0, 1, 1, 0, 1. Okay. That's how. Question here.
Doctor?
Yes.
Yeah, your voice is lagging. I'm not sure if it's from my internet connection or All of
Really?
them have this.
What about the screen? Is it lagging?
Anas, I think is your line because
Ah.
I'm okay.
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 Sorry, Anas. You have
I'm
to
gonna
resolve
change
it.
mine. Okay.
All right. Probably try to log out and log in again. Okay. But I will continue. Okay. The next one is we are given the two's complement and then we want to find the one's complement, sign magnitude, and the decimal. All right. The two's complement here, luckily, okay, it's very easy because it's positive number. How do you know it's positive number? Because the MSB here is 0, right? Positive number. Okay. And as we know, the positive number, the number is this is the same as complement and also the same as in the sign.
Doctor,
Yes.
now your sound is unstable.
Oh, really?
A while is high and a while is low.
Okay. But I really don't know how to solve that.
Okay.
Well, normally, what do you do? Like you
Are you using earphone?
Yep. So when,
I
like
think
my
it's the connection of earphone.
yeah, it happens. Okay, I'll buy another another headset after this. I think if
Okay.
you're using the USB, it's better. The audio jack is always a problem with mine. Yeah, let me know. And as long as the screen is working, is the screen okay?
And screen okay, just the sound.
Yeah, doctor, the screen is okay, and the sound is most of the time is okay.
Most of the time it's okay.
Yeah, most of the time
Right.
it's okay.
Okay. Sorry if you're hope it the you know if it's sometimes okay, it's not, then it's not okay. Sometimes it will trigger trigger the students, like annoying, right? Hope it's okay with you all. All right. So here, okay, I'll continue, right? So here, when it's positive number in the two's complement, or if you're given the positive number in one's complement or sign magnitude, it means you're a lucky day because it's the same. Okay, all the binary in these three is the same if it's positive. Then to find the decimal, you just take the 7 it on the left. So this one is 64 plus 32 plus this one is 8 and then plus 1. So it's 40, 100, 105. Right? Okay. Now, moving on to question B, the Q format. You need to, or not yet. What is the hex number? To binary. This is a positive number. The 2 and so the whole part and the 1 over 8. Then 1 over 8. We have 3, 1, 1 over 8, 1 to 5. 2, 5, 1 to 5. All right. Okay. Next is these questions Q43. Okay, Q43, and it is also a positive number because the sign B is positive, and we divide it to 4 and 3. Okay. And then the whole part is 4 bit number, that is 50. And then the fraction is 1 over plus 1 over 8. So 1 over 4 is 0.5 and 1 over 8 is 0.5. This is 0.375 for the fraction. Combine it. It is 15.375. 15.375. 1, 2, 3, 4, 5, 6, 7, 8, 6 marks. Each of these is 2 marks. And then we have the next question. So the 7 left is all in negative, which means change it. Even right? Change it to normal. Back. First, from the left, first 1. So this is first, and then 1 negative. So negative is 1 over 4, 1 over 8. Alright, but it's negative. Okay. And then C, perform the following arithmetic operation in 2's complement binary arithmetic. Assume 8-bit numbers are used. Okay, so first we change 4 and 12 in the 8-bit binary. Is 0, 0, 0, 0, 0. Minus with 0, 0, 0, 8. Because add, okay, I'm going to use negative minus. Whose complement? 0, 0, 0, 1. Okay. One is changed to choose complement, which is from the left 0, 0, 1, and 8, 1, 0, 0, 1, 1. Okay, I can just find the answer and show it appears here. So 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0, 0. And this is minus 8. Right. So the conversion part is 1.5 and the final answer is okay. Moving on to the next question. Determine the Boolean. Do you need to screenshot the first one? Or you already have? One? No? All right. Okay. Moving on. E for one. This is B and one. A for one. Anything that is always one is one. And this is the complement of one. If B is 0, it will be 0. If B is 1, it will be 1. Okay? So the equation is if the selector 1, the selector is 1, plus if the selector is of the complement of 1 is 0, plus x b x equal to b. And implement this in a single. So there are 3 logic gates. Whether we are using OR gates, B and 0, anything that is OR will be value. In this case, it's B. Or you can add as you want. B is will be or can be. These are the three single gate is accepted for this question. And next, for this one, first you have to solve here. Using the same equation, because this is also here the selector is B. Here is if selector is 0, E bar is multiply with 0 because it's ground plus B, this is AB. And this one, if the selector is E bar 0, okay, and the selector is here it is AB bar plus B. Okay, so right, now the selector is when AB bar B, AB 1 plus, and when selector is 1, 0, AB. Okay. This is 0 because it's multiplied with 0, and then we expand this one. So it's AB bar plus B, A bar plus B bar from the De Morgan, and then you got A bar B bar plus AB bar plus A bar B plus B bar B, right? A bar, that's a 0. B bar, that's a 0. So it left you with A B bar, B bar is B bar, A B bar plus A bar B. And this is an XOR. Okay, done the easy part. So up here is 2.5. So this is 1.5. From here to here is 1.5. And is finding the gates is 1 mark. Here, getting the equation is 2 mark. Expand it is 1 mark. Get the final one is 1 mark. And get the gates is another one. And then come to these questions. Okay, question 3 that is found on the online future website. Everyone almost get 0 for this question because it's found online. But then we discuss and haven't finished discuss. So you have to pray that everyone not going to get 0 for this. All right. So this is question 3. So question 3 says A, B, and C. There are 3 inputs A, B, and C. All of them are 4 bits. Okay, the pseudocode is given below. The pseudocode. All modules. So there are 3 are the modules are given as input. 4 bits is the final output. Build the
Excuse me, doctor.
yes.
Your voice is cutting out. It's not. I don't know. Maybe it's the mic.
Yeah. I don't know how to solve. Okay. So build the gray box with the correct labels. All right. So here the equation, if A is greater or equal to B, then F A plus C. Else if so the complement of A greater or equal to must be B greater than A. Already. Okay. This will be the if and the else. Will depend mode. The mode, right? And here else on G to F and B. Inside here we compare A and B. Right? So here if B is less or equal here in the here in the A is greater or equal to B. But here in the module, if B is less or equal to Q. Right? So which means the A and B is not as straightforward. Is a trick here. which means this is not simply A and B, it is E and A. Here in this here, we are checking please is less than Q, which means B less or equal. So this is not equal. So 1. Greater than A. So this is B. B is connected to P and A is connected. Okay? And GT is connected to mode. Is GT. You can connect the wire or just write GT here. Means it's connected. Same things. Okay? It's also important to make P bigger than as plus we're minus minus. So this we need this mode 1 when subtracting. Agreement. Okay? So then another one, which the selector is depends also on G. So depend. Selector is depending on and uh, here if the GT is 0, here is we want to add A, and if GT is 1 minus A and B. Okay, so A is always in the equation. A is always in the equation, and B and C and B is the selection. In the final, other and subtracted here is A. Okay, this input here is A. Alright, since many of you are complaining about the voice, I am going to try to change the mic. Hello? Is this clearer?
Yes, this one is better.
Oh, okay. Right? Okay. Now let's share it again. Screen. Okay. So this is the screen. I hope you can see it. Where were we? Okay. So A is always in the equation. So A is here, and and C is the selection. Okay. So when mode is 0, when mode is 0, right? This one, when mode is 0, we do the adding operation. So when mode is 0, we add A with C. Okay. When mode is 1, sorry, mode, GT is 1. So GT is also connecting to the cell here. When GT is 1, we are doing subtraction. Okay, subtraction. Where we want to subtract A and B here. So B must be in complement, in 2's complement. So to find 2's complement, minus B is equal to B 1 complement, okay, plus 1. So here is B complement, right? B complement. And here we will add 1 from the mode, okay, from the mode. Because this is not marks, right? This is added. So what coming here is not selector, it is C0, right? Okay, so it is added to A and B. So when mode is 1, okay, the equation is, when mode is 1, the equation is A plus B bar plus 1. When mode is 0, the equation is A plus C. Right? So this is the subtractor when mode is equal to 1. Right? And then the output is F. And then if F is negative, flag F is 1. Okay? When F is negative, flag F is 1. So to find negative number, to know negative number, we have to check the MSB. And this is a 4-bit adder, so the MSB is F3. Okay, so you can connect. This is a bus, 4-bit bus. Connect the 4-bit bus and only take the MSB, F3, or maybe you write it like this, F3. All right, so F3, label it F3 there. This is bus and this is wire, a single wire. So if F3, if F is negative, F3 must be 1. So if F is negative, flag F. So flag F here, which is the F3 is 1, right? The MSB, the sign bit. So this is the answer for these questions. Flag F equal to GT? No, wrong. Okay, flag F must equal to F3 because we want to know if F is negative. So you have to perform the addition first. It's not related to GT. Okay? Now, I want to move on to part 2. This questions is also in the online tutor. Why waste your time? Why waste your 30 minutes, right? You shouldn't put easy question on online tutor because if we decided to eliminate these questions, means like you are already using 10 marks from the 50. Now we only gonna take 40. Okay, this shouldn't be an online tutor. Okay, but let's see what will the last say will be, whether we want to for test 1 it's okay, and let's be much stricter on test 2, and whatever the decision is, I'll wait for them to discuss. Okay. So to do these questions, first you have to But this is how I solve this question. First, I will put inside each gate 5. Node is 5, so it's 5 here, 5 here, 5 here. And then NAND is 10, 10 here. N is 15, 15. And then XOR is 28. And then OR is 7. So you can find A, D, E, F, E. That is, so here is 5. And come to here is 20. This is 25. And 32. Right? And then from B, B, G, if we go B, G, H, I, L, that is obviously less than B, J. So we just going skip this one. Okay, that is obviously less and go with this one. So this is also obviously less, like 20 plus 28. So this is 20, 48, and 48, 7, 45. So if we go B, J, H, I, that will be 10. Here is 25, 25, 28, 53, and 53, 7 is 60. The longest so far. And if we choose C, 10, 15, 28 is obviously less. Okay, so the longest is 60. And the critical path, you have to find the critical path and critical path delay, right? Critical path is B, J, H, I, Y. And critical path delay is 60 nanosecond. Right?
Excuse me, doctor.
Yes.
The critical path can be CJHIY.
CJ, yes. CJ, because it's either of D and C, right? CJHIY.
Yes, it's the same.
Or C here. Same. Okay? Why put so many marks in so simple questions? I wonder. All right. So next question. Yeah, the question that we discussed right away. All right. An example of multiplier circuit to perform multiplication by a constant 12 can be constructed by using a single adder and can be obtained by the operation described in this figure. Right? So you understand this. Here, when we shift x to the right, I3, that we will get 8x, and here we will get 4x. And when we add the 2, we will get 12x. Now, using the similar approach, which is using adder only. Okay. Implement the multiply by 15 function by specifying the bits that go into the 8-bit adder. 8-bit adder. Okay, it must be 8-bit. It must be adder, the implementation. In each of the boxes, enter only 0, 1, x, I, y, I, or their literals, where I is the integer. Enter dash when a connection is a don't care or not used. Alright, so we want to do multiply by 15, and what we know, okay, is we can find the x, okay, 2x, 4x, 8x, 16x, and that's all. That's the biggest. That's the biggest because it shift 8-bit, right? So we can shift maximum 4 times. So that is the maximum, 16x, and we want to find 15. So what we can do is 16x minus x, which is equal to 16x plus x bar plus 1. So implement this. So this is 4x. No, not 4x. 16x. I meant to say shift 4 times. Okay. And this is x bar. So you got 1 from the carry in. So this is x. Shift 4 times. So it's x3, x2, x1, x0, 0, 0, 0. And here is x bar. So it's x0 bar, x1 bar, x2 bar, x3 bar, 0, 0, 0. And then this one is straightforward, y7, y6, y5, y4, y3, y2, y1, y0. And this is don't care. You don't care. So this is the answer.
Doctor, may I ask something?
Mm.
Why the in front of x3 bar is all 0?
Y in front of x3 bar is all 0? Because we want to shift it.
We are
If
not
it's not 0, then it is?
can it be 1? Because it's 8-bit number, so we complement it, so we need to complement including the 0 also.
Correct. Yeah, it's not 0, it's 1. Didn't think of that.
Yeah, but
Very
I
good.
also wrote wrong in SMS.
Oh, really?
I found it later.
Oh, so
Yeah.
this is 8 marks. This is 8 marks, 1 each. And this is 1 mark. This 1 mark. This 2 marks. Okay?
Yeah, still got half of it.
All right. But the percentage, the overall percentage will not be that affected, I think. Because the full mark is 100, right? For both.
Yeah.
All right.
Okay lah.
All right. Now we go to the last questions. Okay. Given an arithmetic function as below, A and B are 4-bit unsigned while Y is a 5-bit unsigned. Okay. It's already mentioned Y is 5 bits. A and B are 4 bits. Okay. Implement the function using the minimum unit of 4-bit adder only. Okay. Do not ignore the adder's carry out output. Do not ignore. You just need to show the block diagram. Do not show the gate level logic circuit. Okay. Show clearly the interconnection and label all inputs and output. Right. So for this one, some of you are using 2 adder, but the answer is actually only 1 adder. 1 4-bit adder, which connect to A and B. So A is 4-bit, B is 4-bit because it's 4-bit adder, right? Okay. And then Y is also 4-bit. And you can add 1 here using the carry in. And B here is simple B. But here we have to shift to 2A. Okay. You can use 2 adder to add A and A, but then this is not minimal. This is not minimal. It's acceptable, but it's not minimal. So when this happen, okay, think of a hardware. What do? You just hardwire the LSB to 0. Connect the LSB with ground. And then this is A0, A1, A2. Okay, A0, A1, A2. So this is how we do the shift without using the shifter. Because it's always 2A, right? Because it's always 2A. So this is your 2A. And this is your B. And the output, okay, Y is 5-bit, right? So this is Y0 to 3. Y0 to 3 here. And this is Y4, your Y4. So that's what it means by do not ignore the adders carry output.
Doctor, is it
Mm.
A is 4-bit number? So should it have A3 there?
Because we want to make it 2A,
Yeah.
2A. A is not a 4-bit number. The adder is 4-bit.
The questions up there is
Here.
that A and B
A, B is 4-bit,
unsigned.
unsigned. But then we want to make A 2A. So we shift.
Yeah, should it be A got 4-bit, so you got A0, A0, A3, A3, A2, A1, A0. So we got another A3 out there. Is it? We shift
So
yeah.
wait, 4-bit, but A is 2A. So it must be because we need to shift it anyway. So A is 0, A2, A1, A0. Then we shift it. This is A. So to make it 2A, we shift it to the left, right? To the right, to the left.
Oh, unsigned, so that so unsigned, so is it we got A3 up as the MSB?
We got A3 as the MSB.
Yeah, I'm confused about that. A3, A2, A1, A0, right?
This can be anything, but we shift it to 2A. So A3 cannot be we cannot have A3. It's a 4-bit.
So if it is shift left by 1, so that the A3 is just ignored already. Is it?
The original A, I mean, right?
Yeah,
The original, because we shift it, right? So from the original A, we shift it, so it will be A3, A2, A1, A0, and then 0 here.
Yeah, that A3 where it been?
We left it out because we want to make it 2A. We eliminate the A3.
Yeah, but I do it in tests like this. A3 I add another half adder to add the C4 and A3, then get it in Y4. I don't know, is it correct or not?
I haven't checked your test paper. I will check it later. I will see what do you mean by adding another half adder.
Yeah, because the most the MSB of A is that I confusing about that.
What are we gonna do with the MSB of A, right?
Yeah, A3. Yeah, I don't know how to do with that.
Oh, okay. Okay, I'll check your paper and then send it back to you later.
Okay,
So
thank
it
you,
is like
Sensei.
no problem. So this is A2, A1, in A0, and then we hardwire the LSB to ground because we shift. This is how we shift. Okay, and then B is also 4-bit, so it's just B3, B2, B1, and B0, and we use the coming carry in as to add 1 here, and the output is 5-bit. So 4 is taken from here, and the MSB is taken from the carry in. All right. So this is A. For B, we want to find the range, right? Based on the circuit in A, determine the range for A, B that produce results in correct computation of Y. according to the given arithmetic, and then determine the range for y also. All right, so A, the range of A is 0 to 7. Because A that is left is A2, A1, and A0. So that's 3-bit. So A, the range of A is 0 to 7. The range of B is easy, 0 to 15. But the range of Y is 5-bit. You can say 0 to 31, but you have to check the equation again. Y is 2A plus B plus 1. When A is 0, when B is 0, Y is 1. So the minimum is 1 and the maximum is when A is maximum 7 to 7 plus 15 plus 1. So this is 14, 20, 29, 30. This is 30. Right? Okay, so
Doctor,
this is
for this
yes.
question, should we consider A3 to get the correct results? Because it says to get the correct result.
Again?
If we ignore A3, then we will not have the correct result, right?
No.
So it's
The
still
A is 3-bit. Accepted. So the A, because we want to shift 1, right? So we have to take only 3-bit. And the 3-bit is 7. Up to 7. 0 to 7. Right? Right?
yeah, but I understood it as if it is a correct result, then you take the whole thing. So like A, you can make it 5 bits. So
A 5 bits? No. A is 3 bits. The original A is 3 bit because the LSB is 0. It's 4-bit adder.
yeah, but the question is to produce the correct. For me, I did same as Jack. I added another full adder to the end.
So you understand it wrong.
Okay.
All right. So C, based on the circuit here, determine the fastest time. So the fastest time, the input can change the value to assure the correct circuit operation. Assume the adder is a ripple carry adder. And each full adder is implemented using 2 half adder where the delay is XOR is 2 tau and AND gate is 1 tau and OR gate is 1 tau. This is the same delay as in our lecture notes. So for ripple carry adder, 1 ripple carry adder, okay, the addition is 10 tau. Okay. Because this is the fastest time the input can change value. So this is combinational, right? Combinational circuit. Okay, combinational circuit. Let's say you have A, B going into a gate, and this will go into another gate. Okay. The fastest you can change input A is when you got the results X here. Okay. The fastest means the earliest you can change input here is when you already got the output here. Means you have to go through the longest delay, the CPD. Right? So for combinational circuit, okay, the fastest or the earliest input can change is after the CPD, after 10 tau delay. Okay? After the delay. But for the sequential, because the X, okay, the output is taken during the clock, right? During the clock. That is for the synchronous sequential. Okay. But for asynchronous, like the combination is mostly asynchronous, and because there's no clock, right? So we have to take it when the CPD has finished. Okay. The earliest is after the CPD. So the question here is just asking what are the CPD of this circuit. Same meaning. Alright? So with that being said, I would like to explain about the sequential logic circuit, okay, which is most of this has been discussed in the video, all right, but the characteristic, which is the timing, I don't think I have discussed it there, so I wanted to discuss it here. Okay. So it's about the flip-flop timing parameter. So the flip-flop is the sequential logic. Flip-flop is the sequential. Oh, this is very thick. Sequential. Okay, so this is the data input, and this is the clock, and this is the output. Okay, so the data input has the setup time. This is what we call as setup time or the input, and the whole time. And then we have the output time here. The data, to be able to, how do I say this? To get the correct calculation in the sequential circuit, the data input must hold it data. If it's 0, then it must hold the value 0. If it's 1, it must hold the value 1. So it must be stable. The input must be stable during this time. Okay. Certain time before the clock. So this is the clock here. The clock arrival here, right? Sometimes before the clock and sometimes after the clock. The sometimes before the clock is called the setup time, and the sometimes after the clock is called the hold time. And then during the clock arrival until some time, okay, is when we take the output. Right? It's the time where we can take the correct output. Okay, if the circuit take the output here after the TCO, then the output is not guaranteed to be correct because the data has been changed and the output might be also changed during this time. So if we want to design a circuit, we have to make sure that the output is taken during this time, and the input must be stay stable during this time. Okay. Setup and hold, where this is the clock arrival. Okay. And this is the definition. The setup time is the minimum time that a flip-flop input must be stable before the clock age. Setup time is before the clock age. Okay. And this is the minimum time before the clock age, where the input must be stable. Okay. Because you know the input, okay, physically is just a voltage. Okay. Voltage 0 and 1. And it can be in between. Right. Hope you still remember about the voltage. Let's say the lowest voltage is 0 and the highest voltage is 5, and this is 2.5. So if the voltage is in this range, the logic is 0. If the voltage is in this range, the logic is 1. Okay, so the gate, the voltage can be stable between this 0 to 0.18, for example. Okay, it is impossible, physically it is impossible to maintain it to 0 volt, but it can be between 0 to 0.18, okay, or maybe 4.5 to 5 voltage, but it must be in this range, means it's stable. It's stable at state 0 or state 1, okay, during this time. If it's not stable, then it will not get, means the timing is violated. Okay, the circuit timing is violated if it is not stable, and that will cause a failure or faulty circuit. Okay. So that is setup time, and the hold time is the minimum time after the clock edge that a flip-flop must continue to be in the same stable state, right? So this is the hold time. Setup time before the clock edge, hold time after the clock edge. And setup and hold is for the input. Setup and hold is for the input to be stable. And then clock to output delay time, or TCO, is the minimum time after the clock edge to obtain a valid output. Okay, it's for the output. Okay. After the clock, so this is the clock arrival. After the clock, there is some time, okay, some minimum time that we call a TCO, or the clock output delay time. Okay, so the circuit, like if you have a circuit that is connected to each other, right? Okay, from here to here, okay, it must be between this time, the TCO. Okay. To ensure that the circuit is synchronous. Ensure that the circuit is synchronous, so we have to take the output that is within this range, within this clock timing. Same goes to here. Maybe this is TCO1, this is TCO2. If it's ripple, if it's not, then this is the same.
Doctor,
Yes.
what is greater than TCO? What will happen?
Or then after the TCO, it is not guaranteed that the output is valid. It could be a correct output, it could be not, because the data has been changed, and then the output could be changed too. So if the data input, so if this is controller and the data input say hold the output, then it will be no problem because the output is the same. But if the data input makes the output to toggle, so after this the output will toggle and you will not get the correct output. So it must be in this range if you want to take the output and connect it to another flip flop or another gate.
Okay.
Okay, so this timing cannot be violated. We have to be in this range. Okay, the output delay. So basically, when you design a circuit, okay, remember in the first class I said in this digital system class we only check the functionality of the circuit. Okay, we will not do the timing check. It's just the functionality. But later in third year, okay, this will be critical for you. So you have to understand it now. Okay, what is the setup time? What is the hold time? What is the output delay? output delay after the clock, right? So again, I said setup time is the time where the input must be stable before the clock age. Hold time is the time where the input must be stable after the clock. Okay? The clock arrival or the clock edge. Okay? So in this case, it's rising edge, so it could be also a falling edge, but it's arrival of clock, right? And then the TCO or the output delay is the time where we can get the valid output, okay, after the clock arrival. Okay, after the delay, we can, of course, we still can get the output, but it is not guaranteed to be correct. Okay, it's not guaranteed to be correct. Okay, so when you were asked, when is the earliest, like these questions right now, right? When is the fastest time we can change the input value? For the asynchronous input, we have to change it after the critical path, after we got the answer here, right? But for a circuit with a clock, such as a synchronous circuit, okay, not a synchronous circuit, okay, we can change the input here after hold. Okay? After hold, we can change the input. Right? After hold time finish, so this is the boundary. After hold time, we can change the input. Right? All right. Now let's check the setup time violation. Setup time violation. So we have a data input, and this is the setup time. If the input violates the setup time, okay, this is the clock. I don't really understand this figure. When the input violates the setup time, there will be two possible outputs. Okay, there will be two possible outputs. Okay, which is output A and output B. We call it as output A and output B. Um, it's just a possible output. So output A means the resolve to new data after. Okay, output A means, okay, the flip flop will resolve to new data, will change to the new data after the output delay. Okay, after we finish the output delay here, okay, the flip flop will choose the new data, right? And for output B, it probably change to the correct data, okay, the new data, but then it will go back to the old data. So that is the possibility. As if you see in the textbook, I'm not sure if it is in this slide or not. Yeah. Okay. The metastable, we're talking about metastable here. Metastable. The metastable state is like when you put a ball on top of a hill. Like when you put a ball on top of a hill, so it can go to state 0 or it can go to state 1. It's not stable. Okay? The stable state is when the ball is in state 0 or the ball is in state 1. So when the timing is violated, okay, there are two possibilities: whether it will go to the new data, which is the correct data, or it goes to the new data and then it reverts back to the old data because it's not stable. Don't know which one to go. Right? So that is why we have to make sure the input data is not violating the setup time and hold time. It must be stable during that period, okay, before and after the clock arrival. Alright. So what caused the metastability? What caused the metastability is because in the real world, our inputs are mostly asynchronous. Okay? Like this traffic light for pedestrian. So your traffic light is basically following the sequence, right? Green, after green it will turn yellow, after yellow it will turn red, and then it will turn green again. It is in the correct sequence, but it can change, that sequence can change when suddenly someone push this button. Okay? That is not in synchronous sequence. It's sudden, so it's asynchronous. Okay? So the traffic light with this pedestrian button, the traffic light itself is a synchronous circuit, but having an asynchronous input. Okay? Synchronous circuit, asynchronous input. Right? So when an asynchronous input happens, we want to make sure that after asynchronous input happens, the circuit will still be in synchronous, in correct sequence, in correct synchro. Okay? We want to synchronize the circuit, even though we get an asynchronous input. So what do? Is we add this circuit. We add this circuit, which is the synchronizer, where when this button is pushed, okay, this flip flop will hold the value here. So this is the asynchronous input. So it will hold this value, and this value will only read when the synchronous clock of the traffic light should be read. Okay. This will make it a synchronous input. So that's why when, I'm not sure if you have experienced this or not, when you hold the pedestrian button, not hold, when you push the pedestrian button, the traffic light not change directly. You will have to wait sometimes, and then the traffic light will change for you because of this synchronizer. Okay, the synchronizer will hold the asynchronous input, which is the button push that you push. Okay, for a certain time, it will wait until it's the correct time for the traffic light to synchronize. So this is what we can do to this is what we can add to our circuit to make sure, or to counter, of to make the circuit free from metastability. Because what happens when we have a metastability, the setup time and the hold time will violate it. Right? So this is one solution for the metastability, and this is another solution, which is a two-stage synchronizer, where we have two flip-flop to stable, to make the input stable before we input that asynchronous input to the system, to our synchronous system. Okay, that is all for today. So you have to watch the video for the rest of the topics, which is the excitations, the intro, and then the bistable circuits and everything. Okay. And I will share with you the test 2 past years of test 2, for you to see what kind of questions that is related to this topic. All right? Okay. So that's all for today. The class is quite short. Okay, for the next class, which is the registers. Right? So next Thursday, we will learn about this. But the data register and shift register will be a video that I will share with you later. This is all repeating or revisiting the digital electronic class. Okay. Then I will straightly go to the accumulator and then the register files. All right, that's all for today. Thank you very much.
Excuse me, doctor. I have a question, if you don't mind.
Yes, Mustafa.
It's about milestone 3.
Oh, milestone 3. Oh, yeah, you messaged me, right?
Yeah.
Okay. What is it? What is the sections, right? Section.
No, I actually
not
figured that out. I just have another, where about. It's about the prescaler part. Should we implement the prescaler using the LPM counter?
Should you implement it using the LPM counter? Is it what?
Because I didn't understand the text which was present in the mini project guide.
1, 2, 3. Which is which part is it?
It's part 3.2.4.
3.2.4. Yeah.
Yes. So I don't get what's bit 25 and what's another bit as clock 2. I don't know which bits should we connect from the counter itself.
This is clock 1 and clock 2, right?
Yeah, the text is a bit it's not clear. It's not that clear. I don't know if it's not clear. I don't understand text. So that's the only part which is left for me. But I don't seem to understand it at all.
Okay. Means we have 2 option clocks.
Yeah, here got 2 clock running at different frequency.
Running at different frequency.
Yeah, for the input filter we got 100 hertz, and for the Night Rider we need 1 hertz. I do like that because the bit is the most LSB we got is 50 hertz. Is synchronous with the system clock, and then the upper bit is 25 hertz, 25 million hertz. Is divided by 2, and then and then I picked 19, the 19 bit, which is almost 95 hertz.
Almost
95
close
hertz.
to 100 hertz.
Yeah, close to 100 hertz. I don't not sure. My circuit is working, but I really cannot get 100 hertz exactly.
It's okay because it said approximately, right?
Yeah.
Approximately means just approximate is okay. So it has 2 clock, and you have to find a way. Maybe
my question is doctor, how should we create the input signal, the clock itself, using the prescaler from milestone 2?
That one is in Verilog version, right?
That one is in Verilog. It says do not use the Verilog. You have to use the counter.
Yeah, my question is how can we create the clock itself?
That's the assignment that you have to solve.
We have to do it using the LPM counter, or can we use
schematic. Using a schematic.
So we can use flip flops or anything, right?
Yes, because it's schematic.
So it's not limited to the LPM counter.
If you think you need another, then yeah, you can use another gates.
Sensei, because I only have one segment display, one digit only, and then can I use the two LED to represent the one at the second bit at the second segment display?
Okay, no problem. But please mention that. I
Okay,
understand. Are you here or not here?
I'm not in UTM. Yeah.
Not in UTM. Okay. Okay, then you can use any resource that you have as long as it is representing the same meaning.
Yeah, I use two LED for that.
How can two LED? Because it's too big.
No. Yeah, for the segment B and C.
Oh, B and C. Okay.
Yeah. So that I use two LEDs to represent that. Yeah.
Okay. Okay.
And like Doctor, one last question for the night rider. Sorry.
Night
For
rider?
like the status signal that indicates when the lights have run a complete round. Like, is there like a certain signal which we should implement, or like should we like just create any pattern on the
Any
night
pattern?
rider itself?
The night rider signal? The night rider sequence?
Yeah, it said
That's
the
the night
ones in.
Milestone 2.
Pardon?
Done the night rider sequence is in milestone 2, right? You have done that.
Yes, it said it wants two modifications. For the second modification, it said it wants a status signal that indicates when the lights have run a complete round. So like, is there like a certain signal which we should create, or like just any signal is good?
Can anyone answer that? Because you have done it.
I have done it. Yeah, I get it from the because we got nine step right in the Night Rider, so we got get the last step so that so when the last step is coming, so done signal will come out and then go back to clear something like that.
Is it like
Just click from the the counter there. We got a 4-bit counter at the Night Rider side. Then so we get it pick it from that, and then we end with something. Yeah, we end the logic, and then give it to and then create a done gate. Also got senior do already got some yeah, you can refer to seniors video also. YouTube on YouTube.
All right, that sounds good. That's good. Thank you, Doctor, and thank you to you.
Okay.